We are now ready to consider instances when the parent population is not normally distributed and we are required to compute probabilities associated with the sample mean. In other words, we're just simply going to learn the conditions under which we can still use this formula that is highlighted on your screen. That is, where we'll be able to claim that the mean of all the sample means is still the population mean, and the standard error is still the standard deviation divided by the square root of the sample size. Under what conditions can we still use this formula if the parent population is not normally distributed? Let us see. You see, in this example, we are told that the following histogram represents the population distribution of 600 horse jockeys. The mean of the population is 116.2 pounds and the standard deviation is 3.9 pounds. And here we have the picture of the histogram. It is very evident that this distribution is skewed right and is far from a normally distributed normal set of values. So this is not normal at all. Well, if we're going to get the sampling distribution of all the sample means, what distribution can we use? What we need to note is this. If we're to consider the sampling distribution of sample means for size 45, take note that this size is greater than or equal to 30. That is, it is at least 30. So, in statistics, this is considered a large enough sample. Because this sample is large enough, we are still allowed to use the normal approximation for this sampling distribution. In other words, the answer to question A, can a normal approximation be used for this sampling distribution? The answer to this question is yes. And the reason is because the sample size 45 is large enough, that is, it is greater than or equal to 30, we are still allowed to use the normal distribution to approximate the sampling distribution of the sample means. So let's write that down first. So to emphasize what we just said, because the sample size n equals 45 is at least 30, it is considered large enough to allow us to use the normal approximation, which is what we used previously in previous videos when the parent population is normally distributed. In a nutshell, all what we are saying here is this. Even though the parent distribution is not normal, as long as the sample size is large enough, that is at least 30, we can still say in question B that the shape of the sampling distribution is the normal probability distribution shape, which would look something of the sort. And of course, that would mean that we'll need the mean and we'll need the standard deviation. So, what is the mean of this sampling distribution? The mean of the sampling distribution is the mean of x bar, and that will be exactly the same as the parent mean. The parent mean was 116.2, so this is 116.2 pounds. And then what is the standard deviation of the sampling distribution? This will be the sampling distribution of the standard error of the sampling distribution, and that will be equals to the standard deviation divided by the square root of n. This is equal to, what is the population standard deviation? It was 3.9 pounds. So 3.9 divided by the square root of n. So we're essentially still doing what we did earlier. The only extra condition is that the sample size must be at least 30 if the parent population is not normal. And 3.9 divided by the square root of 45 is 0.5813777. So let's see another example just to emphasize what we've just said on page 17. Here we're told that the following graph displays the starting salaries for law school graduates entering the workforce in the year 2014. So you can see that this is not a normally distributed random variable. So if we were to describe the shape of this distribution, what would we say? I would say that this is almost saw-like. I do know that this is not a normal distribution at all. It does not look anything normal. Then, question B. We are to consider the sampling distribution of the sample means created from this population using samples of size 25. Can a normal approximation be used for this sampling distribution? Let's look back at the example we considered on page 16. Remember we said that if the parent population is not normal, as long as the sample size you're using is at least 30, you're good enough to still use the normal approximation. However, considering the conditions of this problem, if we are using samples of size 25, it means we do not have a large enough sample. So the correct answer here would be no. A normal approximation cannot be used for the sampling distribution because the sample size is not large enough. In contrast, in question C, consider the sampling distribution of the sample means created from this population for samples of size 50. Can the central limit theorem be applied in this situation? The central limit theorem is simply saying, can you use the normal approximation? The correct answer here is yes. Why? The sample size 50, since 50 is greater than 30, we do have a large enough sample to use the normal approximation for this distribution. So for question D, we are to consider the sampling distribution of sample means created from this distribution for samples of size 200. What would you expect the shape of this distribution to be? Since the size of the sample is 200, which is greater than 30, so this is my argument. Since 200 is greater than 30, I can definitely approximate this distribution or the distribution of the sampling distribution by the normal distribution. So the shape will be a normal distribution shape. And how would it compare to the sampling distribution described in part C? Well, in part C, I have a size of what, size 50, or in part D, I have a size of size 200. First of all, they will share the same mean. They will share the same mean. They will share the same mean, but have different standard deviations of the sampling distribution. So with that done, we proceed to the next example on page 18. An unknown distribution has a mean of 45 and a standard deviation of 8. So this time we just know that the parent population, which is not normal, so I am not going to draw a normally distributed parent population this time. The only thing I know are the characteristics of that population. The mean is 45 and the standard deviation is 8. Now I'm told the samples of size n equals 36, so sample size in this case which is equal to n, is 36. They are drawn from this population. What is the sampling distribution of the mean? So the question is asking, what will mean of x bar be, and what would the standard error of x bar be? All I need to recall is what we have just learned so far. I need to check that even though the parent population is not normal, all I need to check is the sample size. Since the sample size is at least 30, that is, it is greater than 30, I can conclude that the sampling distribution of the means will have a normal distribution still, even though the parent population is not normal, and the mean of x bar will be exactly the same as the parent population. However, the standard error will be the standard deviation 8 divided by the square root of n. That will be 8 rather divided by the square root of 36, same as 8 over 6, which is equal to 1.33333. So, with that said, I have the sampling distribution of the means. It is a normally distributed distribution with a mean of 45 and a standard error of 1.33333. So we'll proceed to the next example. This says that suppose that the prices of athletic shoes have a mean of $75.15 and a standard deviation of $17.89. Take note, we do not know the distribution of the prices of athletic shoes in this case, which is very typical of what happens in the real world. Now, we want to answer the question, what is the probability that the mean price of a random sample of 50 pairs of athletic shoes will differ from the population mean by less than $5? So based on the details given in the question, first, the parent population mean we're given, that is 75.15, and the standard deviation is 17.89. Now, we would like to compute a probability. What we want to find is the probability that the mean price of a sample, so that is the sample mean, x bar, for a sample of size 50, so n is equal to 50, it is the probability that this x bar will differ from the population mean. It will differ from 75.15 by less than $5. What we first note is, to fully interpret this question, we might need a picture to give you a visual aid. So what I'm going to do is I'm going to erase this so that gradually you'll be able to see what we're working on. First of all, note that the sample size is 50. It is greater than 30. So for the sampling distribution of all the sample means x bar, I am allowed to use the normal distribution. And what that means is that I can get the mean of x bar that will be exactly equal to 75.15, and the standard error will be sigma divided by the square root of n. That will be 17.89 divided by the square root of 50, which is equal to 2.53. Okay, now that we have that value, we can then proceed to interpret this question. The probability that the mean price is or will differ from the population by less than $5. Well, that would mean differing will be from 75.15, which is the population mean, by less than $5 would be bounded by 75.15 minus 5. That will give 70.15, and then 75.15 plus 5, that will give 80.15. So we're interested in the probability in this range. So this question means we should find the probability that x bar is between 70.15 and 80.15. Notice that these two values are the upper bounds for values that differ away from 75.15 by less than $5. So to complete this question, I'm going to need the mean and I'm going to need the standard error in my normal distribution calculator. So here's my normal distribution calculator, and I have 75.15 and the standard error. The standard error is 2.53, so 75.15, 2.53. I have both parameters already specified here, and I'm interested in between 70.15 and 80.15. So I'm going to go back between 70.15 and 80.15 and calculate, and I have 0.9519. So that will be my answer, 0.9519. Done. In this example, which is the next example of course, we're told that at a local hardware manufacturing plant, the screws being manufactured have a mean length of 1.625 inches with a standard deviation of 0.010 inches. If the quality control director randomly selects or chooses a batch of 50 screws, what is the probability that the mean length differs from the mean of the population by more than the allowed 0.004 inches? So based on the given information, the population mean is 1.625 and the population standard deviation is 0.010 inches. Now the sample size that has been selected is n equals 50 screws, and we're asked the question, what is the probability that the mean length, so it's a probability connected with the mean, differs from the mean of the population by more than the allowed 0.004 inches. We note that since the sample size is greater than 30, any probability connected with the mean will be approximated by the normal distribution. So it means the sampling distribution will have a normal distribution. So I can draw the normal distribution, and I will be interested in the mean of the sampling distribution. That will be exactly equal to 1.625, and the standard error will be sigma divided by square root of n. That will be 0.010 divided by the square root of 50. And that is equal to 0.001414. Okay, so now that we have the sampling distribution of the sample mean, I can then focus on the import of this question. I'm interested in the area or the probability that the mean length differs from this mean of the population by more than 0.004 inches. What I will do is, from 1.625, which is right here, I am going to measure 0.04 inches to the left and to the right. So that will be 1.625 plus 0.004. So if I subtracted 0.004 from 1.625, I will get 1.621. And if I added the same number, I will get 1.629. So I'm going to draw a line here, and you observe that if all sample mean values are lined up on this horizontal line, every value greater than 1.629 differs from 1.625, the mean of the population, by more than 0.04 inches. That is, the area we want to find here are areas in the extreme tails here, because any mean in all of this shaded region would differ from 1.625, the median value, by more than 0.04 inches. So how do we go about that? The first step will be to find the size of this probability, and the second step will be to find the size of this probability and then add up both numbers. So what I'm going to do then is I'm going to key in the mean value and the standard error in these cases. So in my normal calculator, I've keyed in the parameters of this sampling distribution. The mean is 1.625 and the standard deviation is 0.001414, which were obtained earlier. So I would like to find the area below 1.621. So I'm going to go to below, click on below, and 1.621. I would like to calculate that. That is 0.0023. That is the size of this, 0.0023. And the size of this area will be above 1.629. So here I go. This time above 1.629. And hit enter. That is also 0.0023. So I have 0.0023. And so my final answer for the required probability in this case is going to be equal to 0.0023 times 2 or plus 0.0023. This will be 0.0046. Done. That is the solution there.